You can investigate the motion of a particle which is attached to an elastic spring or string and is oscillating in a vertical line. A particle which is hanging in equilibrium attached to one end of an elastic spring or string, the other end of which is fixed, can be pulled downwards and released. The particle will then oscillate in a vertical line about its equilibrium position. Now, with this kind of situation, we generally find what the extension is to get this equilibrium position, okay? Because then it will oscillate about that point there. And it doesn't matter how you form this, either you pull it down or you drop it from up here, or you give it an impulse from down here. To prove it's got or is travelling in SHM, you draw in the line that, change my colour. You draw in the natural length, you draw in the extension, okay, that is usually classed as E, because it's the equilibrium position, and then you put X, okay, X increasing, and from there then you actually start doing the SHM, Hooke's law and Newton's second law, and then you're away with it. So when the particle is a distance of x below the equilibrium position, its acceleration is x dot dot away from the equilibrium position. At the equilibrium position, the tension in the spring is mg, so using Hooke's law, and it's what we saw last time, you consider Newton's second law, and you're away, and that proves simple harmonic motion. And the reason you would want to do that is to find omega, okay? Now, the particle is moving with SHM because we've got this proof here. Right, as in the case of horizontal oscillations, a particle attached to one end of a spring will perform complete oscillations. If the particle is attached to one end of an elastic string, it will only move with SHM while the string is taut. If the amplitude is greater than the extension, okay, so what that actually means, there is the extension in equilibrium. If you stretch it beyond that, then it will want to complete revolutions, cycles going up to there, but it can't because it's slack at this period here. Okay, so it will only move in SHM while the string is taut. If the amplitude is greater than the extension at the equilibrium position, the string will become slack before the particle reaches the upper end of the oscillation. Once the string becomes slack, the oscillatory motion ceases and the particle moves freely under gravity, so it's just like a projectile, and falls back to the position where the string is once again taut. So that's why the questions get slightly harder. Right, so these are the things we need to highlight. For a particle hanging in equilibrium, attached to one end of an elastic spring and displaced vertically, be it up or down, from its equilibrium position, the particle will move in SHM. The particle will complete full and complete oscillations, and the centre of oscillation will be the equilibrium position. So that's great and all fine and dandy if it's a spring. For a particle hanging in equilibrium attached to one end of an elastic string, however, and it's displaced vertically from its equilibrium position, the particle will move with SHM while the string is taut. The particle will perform complete oscillations if the amplitude is no greater than the equilibrium extension. If the amplitude is greater than the equilibrium extension, the particle will move freely under gravity while the string is slack. Now, a particle can be attached to two springs or strings which are hanging side by side or stretched in a vertical line between two fixed points. The basic method of solution remains the same. Example 14. Okay, so a particle of mass 1.2 kilograms is attached to one end of a light elastic spring of modulus of elasticity 60 newtons and a natural length of 60 centimetres. The length of the spring is attached to a fixed point A on a ceiling. The particle hangs in equilibrium at point B. Find the extension. Okay, so here we go for part A. We'll have the drawing, which is the ceiling, and it's an equilibrium, so we've got the natural length, and then we've got the extended bit, and then we've got our particle, which is 1.2. Okay, and then we've got, that is the force, or its weight component, 1.2 G. We've got tension, we've got that dimension there is 60 centimetres. Well, it's got to be standard index units, SI units, so it's 0.6 metres. And its extension is just here, E. Okay, so we've got that bit there. So using Hooke's law, I might as well put across here that lambda is equal to 60 newtons. Okay. So the tension, which I'll put there, is equal to lambda, which is 60, multiplied by the extension, which happens to be E, all over the natural length, which is 0.6. Okay. Then, using Newton's second law, okay, then what you've got, if we say positive is downwards, okay, you've got 1.2 G, the force, take away the tension, must equal 0 if it's in equilibrium. So I've got T is equal to 1.2 G, which now gives you 60 divided by 0.6, what's that? So 100, isn't it? So it's 100. E is equal to 1 minus 2G. Well, 2G is 19.6, isn't it? Okay, so E is equal to, I've done wrong there, I've done something wrong. Oh, sorry, it's that's 1.2, I can't read my own writing in haste. 1.2, let's start that again. So tension is 1.2 G. So we've got 1.2 times like 9.8, okay, and equals that, which is 11.76. 11.76 metres. Okay, is what that is, and go divide by 100. So E is equal to 0.1176 metres is the extension. Okay, or 12 centimetres rounded up. Right. Okay. So I'll probably say 11.8 centimetres. Right, part B. The particle is now raised vertically a distance of 15 centimetres and released from rest. So this extension here is 11.8. It's a spring, so it's going to be put into compression. Do you agree? 15 centimetres above. Now this is the clue as to what. What is that telling me that is? No. Come on. That's where it's going to oscillate about. If I pull it away 15 centimetres, then what do I know? Amplitude. That's going to be the amplitude. Okay? It's going to go burr, 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 burr. Right. So it says, prove that P will form or move in simple harmonic motion. Now it doesn't matter. You never do it on the full. You never look at one particular example. You generalise it. So with this kind of situation, and listen carefully, I will redraw it again for B, okay? And I will redraw it, and I've run out of paper. I'm just going to draw it a little further up then. Okay, okay, I will draw it like that. I've got 0.6 is there. I always draw the centre of oscillation with a dotted line, okay? And then I will draw it in a position further down here, which is 1.2, okay? But the most important thing is I will usually do X in that direction. Okay, so it's been pulled up to here, and I'll show a certain general situation. It's going to be like that at some stage. Okay, now if X is increasing, that you could do it above it if you wanted to, and then the acceleration will be in that direction because X is increasing in that direction. So it's increasing in that direction there, so it's X dot dot. Right, I've got tension, T, and I've got the weight component there is 1.2 G. So for this, I'm going to use Hooke's law. Yeah, sorry, I've missed that off. That's going to be 0.1176. Okay, so that's meters. That's meters. Okay, so Hooke's law, I've got tension is equal to, at that stage specifically, it's going to be lambda, which is 60, multiplied by the extension at that stage, which is 0.1176 plus the x, all divided by the natural length, which is 0.6. And then, obviously, as per usual, I'm going to do Newton's second law, and I'm going to say it's positive downwards. So I end up with the forces, which is 1.2 g minus my t, is equal to mass, which is 1.2 times acceleration x dot dot. Okay, now t is replaced with this. Now again, 60 divided by that is going to give you 100 on top. So, and timesing through, I end up with 1.2 g minus. In fact, I won't times through yet because that minus is going to screw things up. Just got to be careful. Always be careful if there's a minus in front of the brackets. So I've got 0.1176. I've got plus x is equal to 1.2 x dot dot. Okay, and I really have run out of space now. So I end up with 1.2 g. In fact, what is 1.2 g? I'm sure it works out. 1.2 times 9.8 gives you, SD it, 11.76. 11.76 minus times that again is 11.76. Lo and behold, that will always happen. And that times actually can only be left with x's, otherwise the acceleration won't be proportional to its distance. Okay, negative 100 x is equal to 1.2 x dot dot. They will disappear, and I can just squeeze it on here that x dot dot is equal to 100 minus 100 divided by 1.2 x, and that gives you x dot dot, and it'll have to be a fraction, minus 250 over 3. Okay, so 250 over 3x. And you need to finish off that statement there saying that it's the acceleration is proportional to its displacement and is always facing the centre. Okay, and then I'd say therefore x dot dot equals minus omega squared x. Okay, so that's that bit. That's how you prove simple harmonic motion. Right. If you weren't asked to do this, you would do it anyway. Why would you do it anyway? To find omega. That there is going to allow you to find omega, because that bit there in the middle there is omega squared. Forgetting the sign, that's omega squared. So you go through that process anyway. Right, find the period and amplitude. Well, the amplitude is dead easy, it's 0.15 metres. So let me just get my pen back and go over the page. So period and thingamajig. So 250 over 3, let me go over the page now. I've got C. I've got omega squared equals 250 over 3. Therefore, omega is equal to the square root of 250 over 3, which equals, so I've got square root, fraction button, 250 and over 3. So I've got 5 root 30 over 3. And that is, the units of omega is angular acceleration, angular velocity. So it's rads per second, Okay. And the amplitude, A, is equal to 0.15 metres. They will generally, they virtually always give you that somewhere hidden in the explanation. D, now going back to D, it says, find the speed of P when it passes through B. Now, look at this. B is when it's in equilibrium. B is the centre of oscillation there. That's B, and that is A. So, if that's the centre of oscillation, what does X equal? Have I not worked out the period? No. Oh, I haven't. Sorry, sorry. So I've got period back up here. Tau is equal to 2 pi over omega. Now, omega is this here, so it's 5 root 30 over 3. The 3 comes up and all that malarkey, and I suppose we'll have to work it out as a decimal. Okay, so I need to do fraction button, 2 shift pi, and scroll down and put answer plus equals. That's it, 0.688. 0.688, and it is seconds. Okay, it's a full complete revolution.